this example, we are going to be trying to figure out if have any kind of absolute extremas on this graph, which is a tower function from 0 to infinity. All right, so first thing we want to do is, if we're looking for any kind of extrema, we're looking for where slopes are 0, which means we need to do the derivative of this. First thing we got to do is remember that on a tower function, we're going to adjust it to this look. We're going to turn it into an exponential, and then we'll do the derivative of it. So that turns our equation into e to the x natural log x. And then we'll do the derivative. So if we do the derivative of this, the derivative of e x natural log x is itself x natural log x, and then times the derivative of the exponent. So the derivative of the exponent, we have a product rule in there. So the derivative of x is 1 times the natural log of x. So the derivative of the first times the second plus the first times the derivative of the second, which is 1 over x, and then technically times the derivative of the inside of the natural log. So if we clean all that up, we're looking at the derivative being e to the x natural log x times natural log x. 1 times 1 over x, those things are going to cancel each other, so that just turns out to be a 1. All right, so that is our derivative. We want to take this piece and set it equal to 0. So we're going to do x e the natural log x times the natural log of x plus 1, setting it equal to 0. So we'll set this piece, x natural log x equal to 0, and the natural log x plus 1 equal to 0. All right, so if we try to solve these, first off, an exponential is not going to get you a 0 unless you vertically shift it or anything, and we don't have anything like that happening. So that's not going to get you a 0. Here we can solve this, so we'll subtract 1. Natural log of x is going to equal -1. So how do we solve that? We're going to exponentiate it. So I'm going to choose an exponential. I'm going to turn these into exponentials, just like square rooting both sides, logging both sides. We're going to exponentiate both sides. So I'm going to make them look like that. Because this, as long as this base matches this base on the log, it's just going to turn into x. And then we're going to get e to the -1, which is 1 over e. All right, so we're looking at what is the absolute extrema, which means here's our critical point. So that has a slope of 0. And so if we do ourselves a number line on this, we have 1 over e. 1 over e is some decimal. All right, so 1 over e is 1 divided by e. It's some decimal, 0.37. 0.37. All right, so we're going to test the values. I need the decimal because I don't know what that value is, so I need to know some values to plug on either side. So a value that I could plug in that's smaller, maybe like 0.25, I don't know, something along those lines. And so I'm going to be plugging it into this. One thing about this exponential is always going to be positive, right? And then here we're going to do the natural log of 0.25 plus 1. So the natural log 0.25 plus 1 is going to be a negative. So I have a negative slope on that side. And if I plug in something bigger, which might be like a 1, we're going to do the natural log of 1. I do know the natural log of 1. And because I know a natural log graph looks like this, and that point right there is a 1, 0. So the natural log, so, all right, let's go back over here. So we're plugging 1 into this. That's still going to be a positive. And then we plug in natural log of 1 is 0 plus 1 is another positive. So those are going to be positive. So you have a negative slope transitioning to a positive slope. So that means we're going to have some sort of a minimum going on there. So we'll probably have an absolute minimum because we don't have any graph that doesn't come back down. So we have an absolute min at x equals 1 over e. And we're going to take a look at decimals real quick to see if that agrees. So let me shift my screen. Okay, so if we look at that, we have, this is what our tower function looks like with the x's that are greater than 0. This is our graph. And if I click on that, there's that decimal where we had our 1 over e. So there's our minimum. We have negative slopes. We have negative slopes to the left, positive slopes to the right. And so we had to have a minimum at that spot. All right, so that is using the derivative to figure out where you have some absolute extremas on a little bit more complicated looking equation.